We had with Professor Casciola some discussion about the aim of this course, the way in which one has to organize it, and so on. So I will waste some of your time, always in the hope that you are becoming the highest part of the intellectual class of this country or of Europe, talking about an old problem which is becoming more and more actual, and I discussed this point several times. I will tell you in which occasions later.
You're telling us that Antonio Gramsci wrote a book on tensor absolute characters?
No. Antonio Gramsci, while discussing about the recent reform of elementary school and middle school in Italy in the 30s, forecast exactly what happens now also in this classroom. And he could forecast this in 1929. So the hope, as we are talking about tensor absolute calculus, the hope now is to try to persuade some of you that the painful time needed to learn contravariant and covariant indices is absolutely necessary if you want to become a scientist. You cannot tell, as my students of second year, I want to be a practical engineer, because otherwise you are not here. And you cannot tell, I want to be a practical scientist, because this is an oxymoron. Okay, a scientist is not practical, or it is very practical, because he's so theoretical that he is practical. But this is another thing. So, my opinion, my interpretation about Gramsci is not mine. You can find in the British Journal of Sociology of Education in 1980. The author is a famous expert in education theory. And the title is appealing: Conservative Schooling for Radical Politics. To have radical politics, in particular to have radical academical politics, you need to fight for conservative schooling. Okay, now I will waste a few of your minutes, but in my opinion this is very important that you know this. Okay, so the translation is not mine. I started to do it, but I found a beautiful translation. Okay, so let us read it together. Remark: in search of the educational principle, which is exactly what we tried with Professor Casciola last time. Okay. So we go to the sources. Descriptive definitional philosophy may be a dogmatic abstraction, just as grammar and mathematics are, but it is an educational and deductive necessity. 1 = 1 is an abstraction, but it leads nobody to think that 1 fly equals 1 elephant. The rules of formal logic are abstractions of the same kind. They are like the grammar of normal thought, but they still need to be studied, since they are not something innate, but have to be acquired through work and reflection. The new curriculum is talking about elementary school, but now we can apply it to university, presupposes that formal logic is something you already possess when you think, but does not explain how it has to be acquired, so that in practice it is assumed to be innate. my colleagues start writing tensor calculus assuming that you already know it. And they hide it. And they hide the fact that you need to learn it. Okay? Formal logic is like grammar. It is assimilated in a living way, even if the actual learning process has been necessarily schematic and abstract. For the learner, is not a passive and mechanical. For the listener is not a passive and mechanical recipient, a gramophone record even, if the liturgical conformity of examinations sometimes makes him to appear so. The relation between these educational forms and the child's psychology, don't be offended, you are treated as children, is always active and creative, just as the relation of the worker to his tools is active and creative. A caliber is likewise a complex of abstractions, but without calibration it is not possible to produce real objects which are social relations and which implicitly embody ideas. The child who sweats at Barbara and Baralipton were mnemonic words used to memorize syllogisms in classical logics, is certainly performing a tiring task. And it is important that it does only what is absolutely necessary and no more. But it is also true that it will always be an effort to learn physical self-discipline and self-control. The pupil has, in effect, to undergo a psychophysical training. Many people have to be persuaded that studying too is a job, and a very tiring one, with its own particular apprenticeship involving muscles and nerves as well as intellect. It is a process of adaptation, a habit acquired with effort, tedium, and even suffering. Wider participation in secondary university education. Consider that when Gramsci was writing this, Italy had 30 million inhabitants and 1,800 full professors. Now, Italy has 60 million inhabitants and something like, among full associate and researchers, 50,000 professors at the university. So what was happening at the Gramsci time, that is a large income of students in secondary school, now it is happening or already happened for the university. So wider participation in secondary education brings with it a tendency to ease off the discipline of studies and to ask for relaxations. Many even think that the difficulties of learning are artificial, since they are accustomed to think only of manual work as sweat and toil. The question is a complex one. Undoubtedly, the child of a traditional intellectual family acquires this psychophysical adaptation more easily. Before he ever enters the classroom, he has numerous advantages over his comrades and is already in possession of attitudes learned from his family environment. He concentrates more easily since he is used to sitting still, etc. Similarly, the son of a city worker suffers less when he goes to work in a factory than does a peasant's child or a young peasant already formed by country life. Even diet has its own importance, etc. This is why many people think that the difficulty of study conceals some trick which handicaps them, that is, when they do not simply believe that they are stupid by nature. They see the gentleman, signore, on this term, not of course an exact equivalent of gentleman, and for many, especially in the country, gentleman means intellectual, complete, speedily, and with apparent ease work which cost their sons tears and blood, and they think there is a trick. In the future, these questions may become extremely acute, and it will be necessary to resist the tendency to render easy that which cannot become easy without being distorted. This is the statement by Gramsci which has been forgotten in Italian universities. If our aim is to produce a new stratum of intellectuals, including those capable of the highest degree of specialization, from a social group which has not traditionally developed the appropriate attitudes, then we have unprecedented difficulties to overcome. So, after having remembered this, I have decided that there is nothing to do. You have to suffer. And you have to understand tensor calculus. I am doing this because I believe that highest education is not reserved to the children of upper class. You know, upper class children are now studying in Princeton, Harvard, École Polytechnique, not at the University of Rome, La Sapienza. This is public school directed to those who have no family behind them. So I don't see why in Harvard they are learning calculus of variations with tensor, absolute Levi-Civita tensor notation, and you are not. Okay, so I can agree with you that it is painful, but I will give you some documents, and I hope that you will be willing to learn this tool. Okay? I tell you a story without telling you names. I have in my library a book of a person who was 80 years old when he discovered tensor calculus. As he had written many books about mechanics using coordinates, he was astonished by the fact that he had lost the great part of his life in doing useless calculations, and in order to persuade younger people, he wrote a book in which on the left page you have component-wise formulas, and on the right page you have nearly blank space with 3 lines of formulas, meaning exactly the same thing meant by the left page. Of course, this book is not used by anybody, but he was astonished by the fact that how powerful is the tool I try to sell you. Okay, actually, this is a question of propaganda, if you like. So, we start with a quick exercise. Then we will apply it in several ways. I try to give you pills of tensor calculus in different moments. But please try to understand what we are doing. So, I started, another very bad thing of modern university is that people are using projector for giving lectures. So I will try to go slowly, but I don't want to waste time in closing and starting writing. So we read together the lecture notes I will send you if you give me your mail. So let us start with a linear mapping, which is defined in a vector space TB and having images in the vector space TE. Okay. the transpose or adjoint, if you prefer, of this linear mapping is such that for every couple V and W, V belongs to the starting vector space. Small w belongs to the small vector space. Okay, this equality holds. Now, let us stop a little bit about when talking about this. This definition is depending on the inner product. The transposed is a concept strongly related to Riemannian structure of the vector space in which you are introducing it. Okay, Riemannian structure means you have a vector space and you add an inner product on it. Okay. So, in many books written by careful mathematicians, to this T is added one symbol for one inner product and the other symbol for the other inner product, for underlining that when you change the inner product, you change the transposition. Okay? Okay. Then, once introduced suitable bases in TB and TE, so as we have done last lecture, you represent every vector as a linear combination of these vector bases. Okay, we can represent vectors, tensors, and inner products in terms of their components. So, if we represent vectors with their contravariant components, we said last lecture what I mean with contravariant components, then look, now LAVA means LV, so you are saturating the capital index with the capital index of V, and you have left free the small index A here. Okay, so you have GAB, WB, LA, capital A, VA. So this A is saturated with this A, this B is saturated with this B. The inner product is symmetric, so you don't need to be worried about the order of these small indices. This G means the inner product here. Okay? This has to be equal. This G with capital indices is the matrix representing inner product here. So I use the trick due to Levi-Civita. I'm not changing the symbol G. I'm changing the quality of indices in order to have a quicker and more readable formula. But this is another inner product. This inner product is here. Okay? So I have capital A saturated with V capital A, and then I have the transposed of L, this is by definition, and B, WB. And this has to be equal for every A and for every VA and for every WB. Okay? Now, algebra, we have simple algebra. So I place this on the left side and I factorize VA and WB. And this has to be equal to 0 for every VA and WB. Okay, this is possible if and only if all these animals, remark, B and B is saturated. So A and A is saturated. Okay, so the final animal I have is an animal with 1, 2, 3, 4, these two are saturated. So you have JA, JA index in this, because I have, okay, you are familiar, I hope, with dummy indices. The fact that here I was calling this index B, now I'm calling it with J, I hope. Everybody who has learned Fortran knows that if it is changing in a coherent way the index which is appearing in a do command, it works the same. Okay? So, you know, the bad side of using a projector is that I'm jumping too quickly because I have the formula already written on the screen. So I hope that you are familiar with the statement that if you have a matrix which inner product with any other matrix gives 0, as a trivial consequence of Rouchet-Capelli theorem, it is the 0 matrix. Okay? So this animal is 0. So with simple algebra I can move, look, this side, it becomes this one, because as I told you, you can move the index up with a metric tensor. Okay, maybe I didn't tell you something, so I tell you it now. When I have defined the inner product with the index law, so the index law is eating contravariant components, the habit is to define the inverse matrix of G with the two indexes up. Okay, and what you have to, as the child of Gramsci, to learn painfully is that when you saturate an index with the matrix with the indices up, the metric matrix with the indices up, you get the contravariant or the covariant components of the previous vector. Okay? So, as I want to represent this animal with the index k and j in the right position, all calculations I'm doing are aimed to obtain this result. The transposed operator has, as you have learned by heart, the fact that in the matrix you change the indices. Okay, now I'm showing you that the kj index of L transposed is equal to the kj component of the L matrix. But what is doing L transposed? L transposed is mapping vectors which are small into vectors which are big. So this animal is saturating Wj small up, okay, forgetting a contravariant component of a Lagrangian vector, while the L, this animal here, is saturating the big index. And in order to get this animal here with the big index up and the small index down, you must apply 2 times the suitable metric tensors. Okay. Now, you could believe that this is a pure mathematical game. Okay? However, I will show you slowly that having in your hands these tools, you can deduce in a few pages the equations for the generic Cauchy continuum, while without these tools you need some 100 pages. So this tool is producing a very powerful, it is speeding up very much the conceptual procedure. Actually, I will show you, but this is in principle, it should be forbidden to talk while giving a talk about your own research, because this is not nobody should consider himself so important. But we will talk about cannulate fluids, so somebody else's research, and I will show you how, using this approach, what is painfully deduced with many and complex reasonings can be obtained with simple and linear calculations. You need simply to do calculations. So you don't need to think. You need to apply an algorithm. And everybody knows that deduction via algorithms is the most powerful tool you can have. Okay, but before I attack the principle of least action for first gradient continua, I want to be a little bit more general. Because you can get for free exactly the same results, simply changing a little bit the notation. Okay, these lecture notes are for today. We had enough philosophy, so I will skip Metrodorn. We'll talk about him in another lecture. But what is very important, this is available in internet. I will give you the address where you can download it. We have spoken about this already in our first lecture, but we will come back here. So what I want to discuss with you is a technical calculation. What is astonishing is that following Lagrange and Laplace, I can tell you that every equation of mathematical physics has been obtained up to now in this framework. So this is the most powerful tool we have in our hands for getting evolution equations for physical systems. By the way, this is not my opinion. This is the opinion of this man, who is one of the greatest, Landau is one of the greatest physicists in history of science. And he starts his book, these notes are inspired on his book, he starts his book in this way. Consider that there is some tensor calculus here, because in general we are not sure that our fields are defined in an Euclidean space. Actually, our fields are defined in four-dimensional space-time, at least. So consider mu equal 1, 2, 3, 4. x4 is time, x1, x2, and x3 are the space variables. Now, I must tell you that middle age is very close. I had the pleasure last year, for only 1 year, to teach analytical mechanics to physicists in Napoli. Of course, among 100 students, 10 are very good, but 50 are very bad. And some of these very bad are very, very bad. Why I'm telling you this? When I wrote mu equal 1, 2, 3, a lady wrote 2x in the equation, and in the following deduction, when doing the calculations, he treated the index mu as 2 times the variable. Okay? This happened only during Middle Age. The fact that it is happening now should worry us very much. Okay? So, I assume that I have a Lagrangian density. What is a Lagrangian density? It's a function which maps x1, x2, x3, x4. Then we have a set psi sigma of fields. Psi sigma is 1, 2, 3, n. Psi 1, psi 2, psi sigma, psi n are tensor fields belonging to the tensor algebra I have introduced in the last lecture. So it could be a, I don't know, 5th order contravariant and 3rd order covariant tensor. It can be everything. Look how elegant is this presentation. You have a kinematics whatsoever described in terms of a set of field psi of S. The calculations I will show you are so simple that you may misunderstand them. So I want to stress that they are very general. And here you have the derivative psi sigma over the x mu. So x mu, you have a lower index. So in the choice of Landau, it is covariant component of position vector. This derivative will become contravariant, as we said in the previous lecture. Okay. Now, nature is choosing the shortest path, or the shortest, the minimum of something. So I introduce the action functional u, Gothic u, equal the integral over a domain T of this Lagrangian density. In this context, the formalism is everything. There is nothing else than formalism. So I need to tell you everything in detail, because my experience is that people are copying these formulas without understanding what they are writing. So, for instance, this capital T is a m-dimensional domain. So in case of space-time, you have a 4-dimensional domain. You are calculating the integral on this 4-dimensional domain of this Lagrangian density. We call it Lagrangian because this is a particular family of functionals. This animal is a functional because it maps a set of functions, psi sigma, defined on T. Okay? This operator is mapping this set of functions into a real number. How am I calculating the image? Formula 2 tells you how to do it. You consider the function L. You place in the first m variables the space, time, or the independent variable. Then here, of course it is not explicitly written. Here you write psi sigma of calculated in x mu, and you calculate d psi sigma over dx mu calculated in x mu. So what you get finally is a function of x mu. you can integrate this animal. You integrate this animal, you get a number. So this is an algorithm. You give the fields psi sigma, and when you have given these fields, this procedure gives you a number. Now, why this is a particular class of functionals? Because the value of psi sigma in another point, so if you have 2 point x bar and x, the value of psi sigma in x bar is not influencing the value of the integrand Lagrangian function in x. So when Lagrange proposed this structure of functional, he was violently attacked because people told him that there is a distance interaction, and without distance interaction you cannot describe many physical systems. Now, what is written in all books of Lagrangian mechanics is that this very particular class of functionals encompass all known physics. And for this reason, we must call them with the name of his inventor. I mean, you cannot call it anything else than Lagrange density function and Lagrange action functional, because Lagrange, with this vision, established a set of equations which up to now are able to describe every system we have met up to now. By the way, there are some economists who claim that a more general class of functionals is needed for describing some economical systems. So maybe, I'm not so sure, maybe there is a boundary of the range of applicability of this class of operators. Okay. Now, nature is choosing psi sigmas in such a way that this action functional is minimum. So we have to learn how to calculate the minimum of this functional. Okay. You are not here as a professor of my... When I was a student, my professors would have decided to come and to start the first lecture of the first class, of the first course, with the most general setting, then particularizing this most general setting. I have decided to use the opposite. Do you remember? We have already minimized the action functional for finite dimensional systems. We have already minimized the functional introduced in Timoshenko planar linear theory of beams. So you should have already an experience of what we are doing now. What I want to show you that the reasoning which we have repeated already 2 times can be applied in a much more general setting, which is this one, which is the clever idea of Lagrange. Maybe I already told you, but it is good to repeat. The reasoning I am showing you was invented by Lagrange when he was 17 years old. The idea is the following. I increase of the scalar quantity epsilon my field psi sigma with the modal deformation, with the modal change, I don't know, with the infinitesimal variation given by the form of eta sigma of x mu. So my psi sigma is varied a little bit. How? I choose arbitrarily eta sigma, and then I multiply it times epsilon, which is a small parameter. This reasoning has been generalized and developed by Gateau and Fréchet in 20th century. What is astonishing is that this was done by Lagrange with much more simple analytical tools, which I show you. So the finite delta variation delta, capital delta U, is simply this integral estimated in psi tilde minus this integral estimated on psi. So this is the variation. Okay, if psi tilde is the variation we have introduced before, delta U becomes this. Okay, this is a mistake. I have not yet corrected it. Okay? Now, I call first variation of U this animal, which is obtained by the previous one, simply introducing in 5 the Taylor expansion in terms of epsilon. So the clever idea of Lagrange is, remember, in every book of Lagrangian mechanics it is written the following statement: you will never learn Lagrangian mechanics if you are not able to understand that you can vary one field and its derivative independently before considering their differential relationship. So here you treat eta as an increment of psi sigma, and you treat d eta over dx mu as an increment of this other variable. Okay? And you apply Taylor expansion for this. Of course, you need to calculate dl over d psi and dl over d psi over dx mu. So you have to treat psi sigma and d psi sigma over dx mu as independent variables. You will consider their differential relationship later. Of course, if you have a property which holds for every couple of variables, this property holds also if the two variables are related. Okay, so the reasoning by Lagrange is very clever because it splits the variation of L with respect to psi sigma and the variation of L with respect to d psi sigma over dx mu, treating them as independent, and only in a subsequent step we remark that this animal is the derivative of this animal. Okay? So this is crucial. By the way, if you talk with everybody who got a master's degree in engineering up to 20 years ago, they had at least heard this reasoning. So we are exactly in the situation described by Gramsci. Somebody woke up one morning and decided that a way of an educational method which worked very well had to be changed. I do not know why good engineers need to understand this. But what I know that all good engineers in the past had learned this reasoning. So before changing the educational method, one should think about it. Okay? So I'm treating you a little bit as monks in a monastery surrounded by barbarians, and I try to tell you that this is the fire of knowledge. Please, keep it, because we are becoming old. And soon, we will not be able to repeat again and again these things. So somebody needs to know these things for propagating them. Don't believe that something which is written is propagated. The theorems of Archimedes remained written 1,000 years in books, but nobody understood them, and finally they were lost because nobody copied them anymore. Okay? So we have to understand the theory. So look, the trick we have now. The epsilon is outside. Okay, this is very quick, but I hope that you know integration by parts. So if you take this animal here, okay, consider this animal here. Okay? This animal, if you factorize d over dxm on the left, okay? And then you apply Leibniz rule. The derivative of the product is equal to the derivative of the first times the second not derived plus the first not derived times the derivation of the second. Okay, be careful, don't do as my student who derived sinus x equal, the derivative of sinus x equal cosinus x plus sinus 1, applying Leibniz rule. Cosinus x is, or sinus x is, a function applied to the variable x. Here, this symbol means this animal times this animal. Okay? I'm not writing all contravariant and covariant indices which are saturated, but you can imagine them. Okay? Now, with this trick, you get eta sigma times this derivative times applied to this animal, and then applying Gauss divergence theorem, the animal under divergence here, saturated with nu n mu, gives you a boundary term. This is the boundary of your body, the one where the field psi sigma is left free, because you have one part of the boundary where psi sigma is 0 or given, so you cannot vary it, and a part of the boundary where eta sigma can be different from 0. So I am guilty, believing that this was a set of lecture notes for PhD students. I jumped many algebraic and differential analytical passages. Now, by the way, Euler tried to get this reasoning for 10 years without succeeding. Another thing, do you remember, I hope, that theorem of integrals called Lagrange theorem? There is a theorem by Lagrange telling that if you have the integral of something times something else, and this integral is equal to 0 for every something else, then the factor of the arbitrary field has to be 0. You have to consider that the poor Lagrange not only was inventing mechanics, but also he was inventing the mathematical analysis needed for developing that mechanics. Okay? So, here an expert of mathematical analysis could give a talk lasting 6 hours, because he would need to prove this theorem. Not only, he would be willing to prove that for every internal points of the domain, this equation is true, and that for any boundary point, so for every point on the boundary, this equation is true because you can choose eta sigma, which is very close to 1 on the point on the boundary and vanishing quickly towards the interior, so that this integral is negligible with respect to this integral, so that these two equations are independent. By the way, this is not abstract mathematics. When you will follow the class in numerical methods, you will discover that this point is crucial, because when you try to solve equations, PDEs, using any numerical discrete method, you need to know that you have some nodes on the boundary which are behaving in a different way when compared to the nodes inside, and your boundary conditions are giving the values you are looking for in the nodes at the boundary, or at least participating to the well-posedness of your mathematical scheme. Okay? Okay, I have some objections, but by somebody who is clever, but I don't want to disturb the flow of thoughts. We will discuss about the objections to this main philosophy later. So what is astonishing is that 8 and 9 give you, 8 is a partial differential equation, a set of partial differential equations, and 9 is a set of boundary conditions. Of course, you have some boundary conditions which you are not writing, but are used in the calculation of the first variation. Which boundary conditions? Delta psi sigma equals 0 or equal a given value in a given subset of your boundary of capital T. Okay? In case of material discontinuity surface, instead of 9, you have 2 values on the boundary coming from both sides, and so you have jump of something, because the outer normal is directed in one direction, the outer normal is directed in the other direction when considering the 2 sides of your surface, so you get a minus sign. This symbol is usually used for jump. Okay? Now, 8 and 9 can be called the equations of everything, in the sense that every physical theory which has been formulated up to now can be placed in this form. Don't believe in those who tell you that dissipative systems cannot be placed in this form. Okay? With some painful reasonings, up to now everything has been placed in this form. At worst, you need to modify a little bit this argument using the so-called Hamilton-Rayleigh approach. So at worst, you add a dissipation functional and you calculate the first variation of the dissipation functional. At the end, you will always get first variation of something equal 0. So this formal structure is always given. Okay, now I must defend this approach. I did already in two ways. I've shown you the equation of every discrete system. I showed you the equations of the theory of Timoshenko beam. I will show you many other equations deduced in this way. But I mean, life is short. This course is short. If you go to the book of Moisevich, you find a gallery of, I think, hundreds of PDEs which are deduced in this way. And people who are advocates of variational principles have only one way, which is never conclusive, to defend their point of view. They must show the variational form of every equation, or they must deduce equations for phenomena who were never described before. The power of this method is the following. Every new theory has been formulated in the first instance in a variational form. My experience is the following. When somebody tells you this is not true for a given equation, it is because one book, one textbook, one paper has been forgotten. Okay, if you look carefully, you find the variational deduction of that equation in the literature. Of course, this is an extreme point of view, but I like extreme point of views. Okay? Now, the case of space-time. If the variables are 4, you decide to have, this is a standard trick in Lagrangian deduction, you have so-called isochrone conditions. So your boundary, your volume T here has two kinds of boundaries. You have the time type boundary, which is a boundary where you have T0 and T1, and x1, x2, x3 are free to vary in a given domain. These are, imagine, it is difficult to imagine something in 4 dimensions, but imagine a plane, a 3-dimensional planar form which is closing the top and the bottom of your space-time tube T. And then you have the space type boundary, which is the one in which the variable T is varying. On this space type boundary, you can assume that eta sigma for every T is equal to 0, which means that your fields psi sigma are not changing. So you have assigned boundary values for your fields psi sigma. Okay? Okay, now the integration by parts is working exactly in the same way, and then you get 12, 13, and 14, where here you have isolated the time derivative. The psi sigma over dt is a velocity. It is the velocity of the field psi sigma. Okay, here before I think that we can talk at least another half an hour. But before proceeding, I want to tell you something which makes me crazy. We have inherited, and I'm very proud of it, the Greek attitude towards science, philosophy, technology. And the whole Western civilization, maybe the whole humankind, is in debt to the Greeks for this. However, Greeks were living for destroying each other, and Italians seem to have inherited this very bad attitude. I have carefully searched in the literature. The equation 12, 13, and 14 are available in a book written in 1824 by Gabriel Piola, a mathematician who got his doctorate in Pavia. He was a nobleman, notwithstanding they offered him a chair both in Bologna and in Rome. He preferred to remain close to his properties, so he never moved, but he spent his whole life for mathematics. Okay, I really cannot understand why French are citing only French, Russians are citing only Russians. You know, there is a famous theorem formulated by French. For every theorem there exists always a Russian who claims to have proven it before. Okay? And of course Russians say the same thing for French, and British people are more understating, but of course they believe that everything has been done by them. Okay? I do not know why the typical attitude of Italians is that other Italians never did anything important. This is very, very peculiar. But this is another problem. You need psychohistory of Isaac Asimov and writing the equations of psychohistory for understanding this. It is beyond the scope of this course. Okay. Why I wanted to tell you this? 12, 13, and 14 are Lagrangian. They are not placed in an Eulerian form. Okay? What is crazy is that in the textbooks they deduce in a very clumsy, long, difficult, complicated way the corresponding form of 12, 13, and 14 once transported in the Eulerian representation. When you transport 12, 13, and 14 in the Eulerian configuration, you lose their variational form. So, in 1960, there was an American fluid mechanician whose name is Liu, who wrote a wonderful paper. Fluid mechanics is not variational. Okay, I do not know why he didn't want to read Piola, because you find it in a book written in 1848. If you write directly the equation in Eulerian form, and if you forget they are the transport of something which was born in the Lagrangian configuration, you have lost its Lagrangian structure. And indeed, what you do, you add d rho over dt plus divergence of rho v equals 0, which is the mass balance. The bad news is this is not enough for getting back your variational structure. Okay, but we will go back to this in whole detail. What is important is that balance, if you want, you can call 12 balance of the quantity psi sigma. You can tell that the inertia of psi sigma is varying because of the flux of psi sigma and because of the source of psi sigma. If you feel the need to balance something, okay? Which is a rather twisted need. But, okay, before proceeding, this observation I have found in an earlier book. I mean, sometimes I believe that life, you know, we are like marionettes and we play a role. And this role is repeated after generations. And when you are born in the wrong role, you are bound to do always the stupid things of repeating, being mistreated. Okay, I feel a little bit mistreated as Piola in a sense. Lagrange was violently attacked because of his variational principles. Why? Because many persons, many scientists said you cannot include dissipation in your variational principle. I don't believe this is true. Okay, but as Lagrange, we give up. We say, okay. Instead of formulating a least principle, a least action principle, I formulate the principle of virtual powers, of virtual power. By the way, the name given to it by Lagrange was the principle of virtual velocities, which in my opinion is much more expressive. Now, for a while, take your Lagrangian L. So we start with this action function. You consider your Lagrangian L and you split it in three parts. An inertial one, kinetic energy. An internal one, which describes the internal interactions among parts of your systems, and then you consider an external part, which is describing the interaction of external world with your system. There is nothing bad in this. I mean, I isolate a system. Then I say, this system is interacting with the external world. This system has parts which are interacting one with the other. This system has an inertia. And I split the Lagrangian in three parts. Consequently, the action function can be split in three parts. So we go back and we discover that the action is made by internal action, external action, inertial action. To impose that this animal is minimized by motion means that its first variation is 0. So, first variation is linear. The first variation of internal, the first variation of external, and the first variation of internal actions have a sum equal to 0 for every virtual variation of the fields we are considering. Okay. Now, this formula is very meaningful in my opinion. Which is the step of Lagrange? He says, okay, I forget about 17, so I forget the fact that my first variation is the first variation of something. And I remember only, I keep only the fact that it is a linear functional of the virtual variation of my fields psi sigma. And I call this linear functional the internal power if it is describing the internal interaction between parts of the body. The external power and the inertia power correspondingly. So, in a sense, I relax the assumption 17. Instead of assuming that the internal power is the first variation of something, I postulate it directly. And similarly for the external power and the inertial power. In this way, you get easily also dissipative systems. So you can formulate the principle of virtual velocities or principle of virtual powers in a way. You can say, I want to know, we are back once more to the first lecture. I'm giving you more details. When I want to find a mathematical model for a physical system, the prescription given by Lagrange, Piola, everybody accepting the variational approach is the following. First, you describe the kinematics of your system. So you introduce the domain T and the set of field psi sigma. La cinématique d'abord. This is the war cry of French orthodoxy, okay? Which is not French because Poisson was French and he didn't believe in it. The war cry of variational people, okay? So once you have introduced the kinematics, then you say, how is my system interacting with the external world? I conjecture a shape for Px. How my system is interacting better, how the different parts of my system are interacting one with the other, and I add P int, which is the inertia of my system, and I add P inertia. So, from a conceptual point of view, Lagrangian strict orthodoxy is more economical. It is enough one Lagrangian function and you describe everything. While if you want to assume the weakened form, the principle of virtual velocities, then instead of using one functional, you need to introduce three. One for every sort of interaction. Okay? It is clear that Lagrange was really bored by the opposers, because in a given moment he says, okay, instead of postulating a principle of least action, I decided to base everything on the principle of virtual powers. So nobody will complain. This was not true because people, then we start next subject. I told you that you should read Lucio Russo's book. Please do it. I give you a Rousseau-like interpretation of this part of mechanics. You have somebody skilled. He invents a new theory. In order to formulate the new theory, he starts with kinematics, then he introduces an action functional, he painfully calculates this in the result of integration by parts, and he gets some balance equations. Then he tries, which is earthy, to give a physical meaning to what he's doing. So what he's doing? He interprets this as a inertia or inertial force. He interprets this as a flux of something because you have a divergence. He interprets this as a source term. And look how beautiful is the structure. Only flux is appearing on the boundary condition. So this is important. I don't deny that when you write the Lagrangian for a material particle, 1/2 kinetic energy minus potential energy, you calculate the first variation of this, then you interpret mass acceleration and you interpret the external force applied on this particle as something to which you could give a physical meaning. But what happens is the following. The calculus of variations is abstract. You need to conceive a functional. You need to conceive a space of functions. Remember this. When you look for minima and maxima for a given function, you need to tell where you are looking for minima and maxima. So you have to give the domain of this function. When you have functions of 5 variables, more or less you understand what you are doing. When your domain is made itself of functions, you have a hierarchy of ideas. You have a domain T. On this domain T you have a set of fields psi sigma. A given set of fields psi sigma is the domain of your action functional. Your action functional is minimizing through motions. So motions are those fields which minimize the action. So you have 3 levels of domains and functions. You have a set T. You have fields defined on T. You have a functional defined on the set of fields psi sigma defined on the set T. Okay, this is difficult. Okay? This is clearly an abstraction which is difficult. So, somebody, for the theory of continuous body, I can tell you name and surname. Oh, I can tell few names. Cauchy, Navier, Poisson. Do you know what they decided to do? They woke up one morning and they postulated 12, 13, 14. So they dramatically simplified the exposition of their theory. When studying fluid mechanics, they did worse. Instead of postulating 12, 13, and 14, they transported these equations in the Eulerian description and they postulated the transported equations. It has to be understood why in Berkeley they call the transformation from Lagrangian to Eulerian description Piola transformation, giving the right credit. So I was astonished. When I was speaking with a colleague, David Stegman, in Berkeley, about my discovery of Piola, he told me, I know, This is Piola transformation. So I said, how you know it? I said, I don't know. So we looked carefully in his books. We couldn't find. So oral transmission reached Berkeley, and somebody knew, maybe Nagdi, somebody knew that the equation 12, 13, and 14 must be transported in the Eulerian coordinates for getting diversion applied for fluids. Okay? So I strongly suspect that somebody decided to make a simplification like that one made in our high schools, in our courses of mathematics nowadays. Instead of painfully fighting with the right postulation, they gave you the final result. Now, why this is very bad? This is very bad for practical reasons. I try to explain you. If in your hands you have only the tools of mathematical analysis, think about the fluid of the flow of a viscous fluid in a pipeline. Okay, you work with the differential equations, you find some profiles. And engineering practice has been guided by these solutions. Or if you want to design beams, you use Saint-Venant solutions, and you get some information about your system. So, before the computer, it was practical to teach to students directly the equations 12, 13, and 14. Because in practice, you need them. Okay. Now, another variational man whose name was von Neumann, in the 40s, he invented the von Neumann machine. Computers. How are you calculating the solutions of partial differential equations? Think how clever are these people. They postulate 12, 13, and 14. They multiply it times eta sigma. They integrate by parts. They get this. Then they discretize eta sigma and psi sigma, and they minimize it. This is the final proof of how the human brain can be twisted. You need the variational principle for doing calculations, but you don't base your theory on what you need. Of course, there is a reaction to this. There are some mathematicians who never write divergence of something. You must kill them. They only write problems in the form min something and the domain where you are looking for the minimum. This is the reaction to this other schematic, too extreme point of view. So there are some mathematicians who are proud of the fact that they have never seen the Laplacian. They minimize grad u square. Okay? And they never pronounce the word Laplacian. So, the message is the following. I've done. Yeah. So the message is the following. No, don't worry, we cut everything. The message is the following. If, I hope, you will need to invent a new model. Somebody gives you a set of phenomena which nobody described before. And they ask you, of course, what happens usually is that they give you some equations. They tell you this equation is forecasting this. For instance, D'Alembert paradox. You have Euler fluid, you calculate the force, resultant force on an obstacle, and you discover that this resultant is 0. So you discover that ships are not existing, airplanes are not existing, birds cannot fly, and things like that. So of course we are not followers of idealism, so we believe that reality is stronger than our ideas. So we change our model, we don't stop looking at the phenomena. So we introduce Stokes-Navier equations, which are newer equations in which D'Alembert paradox is not anymore valid. Okay, so what happens? You have a model, it is not forecasting something, you have to improve the model or invent a new model for describing new phenomena. Okay? Now, the message I want to send you is the following. In the past, up to now, the great majority of new models were formulated in this way. When you need to formulate a new model, you introduce new kinematical descriptors, a new Lagrange function, you calculate its first variation, you find the new equations. This is what has been done up to now. Of course, nobody knows what will be done in future. But think about this. If you want to find numerical solutions, you don't need to integrate by parts. These equations are useless. You write your functional. You calculate its first variation, you implement your code. You don't need to talk about balance equations. So why doing something useless? Forget about it. Write your equations in weak form, that's it. Okay? Of course, again, this is all violent polemical point of view, violent argument. I will show you in the next lecture how Piola is deducing the equations of continuum mechanics. So I prove you how it has been done. Okay? Okay.